slide, so I just request a control.
Great. And can you introduce yourself? Because I know you're not Yanda, and I'm sorry I missed your name. I was talking over.
Oh, yes. My name's Yanda Zhang. I'm with ZYD Energy. I'm the CEO and founder of the company. Yeah.
Fantastic.
Should I go ahead, start the presentation?
Yes, please. Thank you.
Yeah. Well, thank you for the opportunity. You know, feel free to stop me at any moment during my presentation. I'm kind of not very good at multitasking, so should I also look at the chat if questions pops up?
No, we'll take care of that for you.
Okay, great. Yes. Okay. So yeah, today, let me see. It's okay. It's moving. Maybe it's just a lag.
Yes. I think that, I don't know if you've taken control, because, have you taken control? Press that button at the top.
Oh, let me see.
Right next to the chat, it says take control.
I request control. There's not a button that says take control, but I can click on a button here and yeah, I can move it.
Great.
Yes. Yeah. I guess I didn't see the first slide, but that's fine. That's fine. That I think the title slide somehow was missing. Maybe it's on my fault. But anyway, I'd like to present a heat pump water heater system integration and control solution to the group. So we know central heat pump systems are complicated, and it is a major kind of adoption barrier, which cause high cost and performance issues, make the system difficult to maintain, and also make the overall central system less scalable. There are two types of solutions that I see currently trying to address this issue. One is to have comprehensive design guidelines, especially the ones like NEAR's developed, and AWHI also has an effort to develop some similar design guidelines as well. The other approach is to have a skip system that have all the different components packaged together. For example, I'm showing here an example, the skid system divided by a water drop. And I think both solutions that definitely have made a huge impact on the adoption of central systems. So what we like to have is another kind of solution here, what we call locus flow router. Locus stands for load optimization control using storage. And the concept of this flow router is similar to an internet kind of router. And we're all familiar with that device. It makes the internet connection much simpler. All we need to do is connect all the devices and computers and to a router. And the router manages all the data flows and things are connected. Very simple. So similar concept here. What you can see in this diagram is that we have a locus flow router. Basically, we kind of routing flows. What the system can be established simply by connecting heat pump water heater or other heating equipments and hot water tanks or other type of thermal energy storage to this flow router. It's kind of plug into this flow router. And then the flow router is going to manage the flows among those equipments and establish an overall system operation. And each flow router also has control and connection to a IoT-based cloud system to manage data. And each flow router can receive grid control signals directly from the source or through this IoT system to make the system to achieve load flexibility. So this is kind of the overall concept, is a way trying to make the system architecture to be simpler and and also make the system more versatile. What you can see is that it's not limited to one type of design, and you can have, kind of mix and match of heat pump water heater or other heating sources and different types of storage equipment. So this is kind of our approach to achieve a kind of plug and play system design. So here is an example of a flow router showing what's inside. So basically, we have some electric valves and pumps, and kind of strategically designed in a way that we can achieve versatile flow management. And then we also have a basically custom-made controller powered by a microcomputer, be able to manage the operation of pumps and valves, and then overall to achieve the flow management. So now, with this configuration, what we like to achieve is what we call a system level control. To a degree, it's more towards a system level of thermal energy storage management. And I'm showing a couple kind of diagrams to give you to show the concept is that, we can have one system operation mode such that hot water is kind of transferred from the heat pump and to the storage, right? Therefore, it's a kind of a charging process for this for the storage. And we can have another operation mode by changing the valve and pump configuration inside the flow router, right? Such that we only use the storage to meet hot water demand, right? So we can also have another option mode that only use the heat pump to meet the demand. Save the hot water storage for later, for example, a peak period, right? We can also, right, have the storage idle once it's empty so that we can later on use this empty storage to kind of trigger more heat pump operation, right? To trigger energy use during the period when the price is low or renewable energy is available, right? And we also have what we call a default mode that is just kind of safe mode in case there is any failure on the control side and the system's not going to work, right? So the concept is again not limited, not trying to manage the control of individual heat pump orders. Instead of focus on the overall kind of the system operation. And because the control is achieved by managing the flows through the heat pump water heaters, so we don't really need to directly interact with internal controls of heat pump water heaters. Therefore, so this solution is kind of compatible with all heat pump water heater equipment. So with this, in a sense, like a hardware setup, so the next level we have is a optimization algorithm that utilize kind of the versatile system level control that we have, then to achieve the optimization. So the optimization will based on a system kind of model, not the complicated, performance model, but rather some high level, energy model of the system, and also taking considerations of the electricity price or other type of grid control signals, also including possibilities of using kind of electricity carbon intensity signal for the optimization. And the optimization certainly is going to take considerations of the hot water demand forecast. And right now, we don't yet have a kind of sophisticated algorithm to forecast demand. But going forward, we would like to have more kind of smart algorithms that adjust the operation based on the demand forecast. So, And then the control is based on a kind of comprehensive measurement of the system performance and enabled by the sensors included in the flow routers, which also give us the opportunity to use the same data, right, to achieve more comprehensive performance monitoring and fault detection. So I'm here just showing kind of a chart as a kind of example to showing how we can utilize the data that is collected by the flow router and then managed by our IoT system, right? So that will give us the capability to have performance monitoring and the kind of the in-depth diagnosis of potential issues. So with all these features and capability, what we think the value that we would like to provide to customers, to our partners, is really, I think the key is trying to reduce cost, reduce the upfront cost and operation cost. What we see is that kind of the simplified diagram, the architecture, right? Hopefully we'll be able to make the design process, installation and commissioning process all simpler. Because from a designer point of view and installer's point of view, right? Kind of that the architecture is very easy to understand. The designers, all they need will be focused on the kind of equipment selection and sizing. And then the plumbing and the connection side will be kind of mostly achieved by what's inside the flow router, right? So on the operation side, because of the kind of optimization of algorithms and also the kind of the performance and monitoring and fault detection that help us, right, to reduce kind of the operation cost over the long term. And in addition, this architecture help us to increase the scalability of central systems and really helping us to kind of achieve the goal of reduced greenhouse reductions and with impact by using the kind of advanced control that we have. So now I'd like to show you some examples what's happening in the field. And here, supported by a CEC EPIC grant, and we demonstrate this technology in 3 buildings. The wall project was led by Redwood Energy and also supported by Ecotope, and we basically provide the technology. So 3 types of building. The first one is 14 units. In fact, they have 1 Sanden heat pump water heater to serve 7 units, and another Sanden serve another 7 units, so 2 system total without recirculation system. So what we retrofitted system is to include a flow router, what you see here is kind of whitish box, and add additional storage per eco-sizer for achieving load flexibility. So this is 1 system. And the second system that we have a building 3 stories high, but this building use kind of clustered, heat pump water heated system designs such that they had 1 Rheem 65-gallon heat pump water heater plus another Rheem storage tank 80 gallon, and to form a kind of small central system serving 5 to 6 dwelling units. So there are basically 12 of those small systems inside this large building. And so we retrofit the system by adding a flow router. And some of the systems we include additional storage. Some of them we didn't, just kind of use the existing storage. So the third example is for a large central system. This is kind of a 4-story, 75-unit apartment in Gilroy, which currently is served by two COMAX system. And so the retrofit add a flow router here, and then add additional storage per eco-sizer for load shifting. So the result here, and for the first example, small building using sand and heat pump weighted system, right? So first test is for using a time of use rate provided by the LBNL. And the baseline, the solid blue line and orange line, and you can see, well, there's at least some energy used during peak hours, and with locus flow router, and the dashed line shows that the kind of the peak energy consumption was significantly reduced. And from a cost point of view, again, this is not the real utility cost, but rather based on this kind of like a testing rate, right? The overall cost is 71% or 72% among those two systems, between those two systems. And this result is published in one of the AWHI summer study. So next one, same site, when we try another rate plan, again provided by the LBNL's CalFlex Hub, what they call is a winter rate, basically two peak rate. And again, solid line shows kind of the baseline operation, energy consumption profile, and then the dashed line shows the result under locus flow router control. You can kind of see that during this large peak, the dashed line definitely had a lower energy use and more energy use being shifted to when the cost is really low, right? And there's also a small increase of use when the price was relatively low, but not the lowest. So the overall cost reduction based on this rate is one is 37%, the other one is 64%. Now, this is another system, right, for the kind of the Eureka side where they use the clustered system. And here we're showing the test result by using LBNL's what they call summer HTP rate, basically summer rate where you have a very high peak during the afternoon hours. This system has both heat pump and electric resistance heating, right? So you can see that when the price was really low, there were increase of electric resistance heating to kind of load up the storage. But there was also increased use right before this peak here, just so that to kind of enhance the kind of storage increase, right? So that during the peak, energy use can be substantially reduced. Another example showing this is kind of the LBNL's spring rate. You can see which is pretty much our current time period, right? Springtime. And during the middle of the day, the price is really low, that heat pump and electric heating was really significantly reduced to basically increase the storage. So this result is also published, which is in one of the presentation of doing the AWHI summer study just happened the last month. So another example I like to show is that this is not necessarily the core kind of control function of flow routers, but flow routers can also provide improved recirculation control, which turns out to be very useful for certain situations. For the Eureka case that I explained, that they had cluster systems. Because the overall system is very small, it was more feasible to use recirculation controls. In fact, the site had recirculation control. It just sometimes it didn't work very well. So what we're showing here is with local flow router low shifting, which reduce the kind of peak hour energy consumption, and also the kind of the improved recirculation control, we significantly reduce energy use. In fact, it's almost pretty much 50% energy use. Most of that was actually through recirculation control, not through the low flexibility control. And so switching a topic a little bit, I'd like to just show you the example of how we can use this solution to just some of the kind of the market application needs. And what we see, for example, a lot of existing buildings, multifamily buildings and commercial buildings, right? And it's very common to use for example, one gas commercial water heater for serving a building. And 100-gallon commercial gas water is very common. And they're usually in a closet, right? So in fact, this is an example that we have for a real building for one of our clients. That the question is, how do we retrofit this system, right, to heat pump water systems? So what are we proposing or provided here is using a flow router and then using the existing gas water heater just as a tank, basically to kind of remove the burners, decommission it as just a storage. And then we add another standard storage, 119 gallon, coupled with several compressors. Really depends on your building size. Small ones, you may want to just use 2 compressors. In this case, we have 3. In another case, we could have 4 compressors. So, so the way we are using this gas water heater tank here, it's in a way it's a bit unique that we all know that for recirculation system, especially for single pass heat pump water heater, right? We better have a swing tank. But the downside, well, I wouldn't say a downside, maybe a consideration, right? For this application is that if we do need to add a swing tank, we need a kind of, in a sense, a dated tank and then space for the swing tank, which is going to be challenging for existing buildings. So with flow router technology, we are able to use this tank as both a swing tank and a primary tank. Therefore, kind of the somewhat reduced overall storage requirement and basically literally just the space requirement. The way we use it is during kind of normal hot water demand period. This will be used as swing tank, and then during the peak, and this control will switch it into a kind of primary tank, which can be also used for serving demand. We also have a small tankless water heater, electric resistance tankless water heater, controlled by the flow router. So give us additional leverage, right, to supporting recirculation system when this, when the how should I say, the hot water demand is not able to provide enough energy to support recirc. That's kind of the concept of swing tank, right? We like to use the hot water produced during the hot water demand, right, to support recirc. Sometimes hot water demand is low. We do need to have other heating sources. That's why we have a tankless electric water heater, coupled with advanced recirculation control. Again, only applicable for small buildings. So this overall system, our cost met that is delivered cost is about $4,000 per boiling unit. And I would like to also point out that the flow router certainly is right now we're focusing on for central heat pump bodies for multifamily buildings, but we should point it out. It's a integration and control platform, right? So it also allows to consider how do we integrate system for other purpose. For example, combined space conditioning and water heating system that requires quite a bit of coordination between heat pump operation and storage. That's what we kind of are to a degree is good at, right? Is to coordinate the operation of different equipment. And also we can use it for systems that have hybrid heat pump and natural gas water heating, for example, for cold climate, when you have many cold days that a heat pump may not be able to provide enough hot water. We also kind of looked into actually studied and demonstrated that how we can use this technology to integrate heat pump water with advanced thermal energy storage, for example, phase changing material-based thermal energy storage. So that's basically concludes my presentation. Yeah, thank you, and have my contact here. Have any questions? Yeah, feel free to contact me. And also, I'd love to kind of collaborate with all of you to do more kind of interesting works. Yeah, feel free to contact me. Thanks. Questions?
Hi, Yanda. It's Josh Blitzbaugh. I was wondering about the electric tankless water heater and the design you showed like a couple slides ago.
Yeah.
Do you happen to know what the KW is? How many kilowatts that pulls, that draws?
Yeah. Kind of depend on building size, but this system, what we're looking here is we're targeting building size between small, like say 6 units, up to 16, 18-ish dwelling units. Again, depends, right, the dwelling size. Eco-cider, if you're assuming heat loss, recirculation heat, 100 watt per dwelling units, you need about let's say 1.6, 1.5 kW, right?
Okay.
But for small buildings, it could be less.
Okay.
So in general, I think will be less than 2 kW.
Great. That shouldn't be much of an issue then for the load.
Yeah, less an issue for you to use, for example, a multi-pass or kind of a residential style heat pump, right, which is like 4.5.
Right.
Any other questions? Okay, we have Bonus has a question, says, for retrofitting, what are the safety requirements if the unit has an A2L refrigerant?
Oh, sorry, I missed the last part. What
are the safety requirements if that's going to be installed in a retrofit situation if the unit has an A2L refrigerant?
Oh, I think it's probably beyond what I'm talking here. So I don't know how to answer that question.
That's okay. That's all right. So we'll table that one. And did we already address Scott's question earlier that says, I don't think we did, what type of recirculation controls were used to save 50% in the example?
Oh, okay. Yes, good question. So the site had basically aquostat control, basically had a temperature sensor attached to the hot water return pipe, and which use a dead band between 95 or 105. Basically, when the temperature dropped to 95, on the return pipe, it start the pump, right? And once the pipe temperature reach to 105, the pump will be stopped. What it didn't work out quite well is that, one is the temperature sensor sometimes it just does not attach very well to the pipe, but no one really knows, right? Because you don't exactly know. Or over time, that contact it began to be loose, it make the recirculation just running 24/7. So what we came in is really just kind of implement the same approach but with more reliable sensor measurement within the flow router. That's kind of one. And then also because we have more kind of being able to implement more sophisticated control logic. So we've set the time limits. For example, if the pump doesn't run for say 3 hours, we know something's going wrong. It's probably the pump need to be run. If the pump runs, but it's more than, in this case, more than 20 minutes, we think it's excessive, right? So that's a safeguard, the time limits. The third one is that it will based on kind of demand. During high demand period, for example, you have a long shower, we can detect that, and the system is really already kind of supplied with hot water. The supply pipe should be hot. And we can then reduce the recirculation accordingly because, right, the hot water use itself serve the purpose to heat up the pipe.
Thank you. Then there's another question. Jim wants to know, can you run the gear in non-router mode? So you can see the baseline of the hardware without the flow router.
Yes, I kind of explained it. All our flow router has a default mode. That is not necessarily what you see. The default is basically saying it's not a control. The system, the control doesn't run at all, but people will still get hot water. But this is not necessarily the so-called baseline, because the baseline for existing system is whatever the existing design or the installer come up with, right? It's not this default. But for the CEC study, we did install the flow router in a way that can be completely bypassed. Therefore, will be the default mode or the original baseline mode.
Thank you. Thank you. Well, we are running a little over on time, so I want to leave some time for Amin to share. Thank you, Yanda, for coming and sharing. Really valuable for the market and help with
No
costs.
problem. Thanks. Yeah.
Amin, are you ready?
Yes, I am. Yeah.
Okay, let's move. You want to take control and then move forward in the deck, or would you like me to try to?
Yeah. Let me see if yeah, it's allowing me to advance. I can get to the slide here. Okay. Yeah. So excuse me, it's really great to be with everybody here today. This was also similarly presented at the Hot Water Forum, and just happy to kind of share this information with this group. Yeah, we're going to be talking about, system design, sizing, and the policy research that's been going on to decarbonize the water heating in commercial kitchens. And, to kind of recognize some of the project funders, the PG&E Code Readiness Program, they conduct research and also fund lab and field research, and do a lot of planning, in fact, to support effective code development. And we I also work on the case team. We get to utilize all that data and develop new code. So it's a really effective overall process. And in this project, we've had a chance to also work with CalNext. They fund a lot of electric projects to identify, test, and grow these technologies. And they also want to they're there to support California's decarbonized future. So it's been really great to work with them. And we also worked, our project partners are the Applied Technology Services Laboratory that's at PG&E, and also 2050 Partners and Frontier Energy. So moving on, just speaking to kind of really the importance of food service segment and decarbonization. Food service is one of the most energy intensive building types. As you can see, fast food and sit down are well over 300 kBTUs per cubic feet. And if you look at all the lighter green bars, you can also see that there's a lot of significant high use energy intensity in food service. And with this table, you see that it's across the board. It's in many non-res segments and institutional segments. Focusing back on food service, there is not a lot of profit. They have a very short payback focus, and these businesses don't always, they have high failure rates. So it's a very challenging environment for this technology. But ultimately, we want to decarbonize food service, and that's related to the cooking equipment, space heating, patio heating, and of course the water heating. And that's what we're going to focus on here. When I was in the lab, I used to say that even though we're very much cook line focused when I was working at the Food Service Technology Center, but per appliance, water heating is the single highest energy using appliance in the average restaurant. So that certainly is the case. There's lots of sanitation going on. Some of the early research we did really kind of got us going. We, about 25 years ago, we started looking at the water heater. And over time, we're like, oh, there's a lot more going on here. We need to look at the research system. And, just kept expanding to really understand that the water heater is really a system and that there's a lot of things we can do. And some of the things that was really exciting was in 2018, we did our first full service restaurant research system project. The tankless heaters in that site were not working well with the research system. We were able to size down the recirculation system and also add demand controls. And we also decentralized the bar and the bathrooms with point of use electric, and then put in a heat recovery dish machine that worked off the cold line. And all those things allowed us to size down the research system, maintain condensing function of the gas water heater. And it was our first case of kind of decarbonizing hot water systems and also electrifying hot water systems. And that kind of led to, I moved on to the PG&E labs and worked there doing testing on heat pumps in the laboratory. About that time in 2021, I recognized that there was a huge barrier for decarbonizing past kind of the residential spaces into food service. And so that was kind of where one of the biggest barriers we highlighted was the health department barrier to heat pumps. And we can get into that in a little bit. Fast forwarding 4 years, I had moved on from the lab, and at TRC currently, we worked with the Decarb Coalition, Ted Tiffany, and he connected us with a project where they could not get a heat pump into a decarbonization project at this university. And we saw firsthand that. Sorry.
Somebody need to go on mute.
Yeah, we saw firsthand that that there was a significant barrier there, and we were hearing more and more about rejections of the health department. So that was really the big catalyst, and we got some efficiency programs involved and worked with CalNext specifically to fund some research. Specifically, we have completed some of these projects. This includes the market potential for heat pump assisted hot water systems. And we also developed a technical design guide. We updated that guide. It's in its 3rd edition. And we also completed a master mixing valve project. And so those are just some resources for folks to check out. And we can talk a little bit more about them. So one of the first projects was this market potential for heat pump assisted systems. We will utilize some CEC research that showed that essentially California is 90% gas, 10% electric, and the biggest loads are in your sit-down restaurants and your fast food restaurants. And that has changed since COVID. There's less sit-down restaurants, and they have been going more and more out of business. And fast casual is kind of a new emerging segment, which is kind of right between fast food and sit-down. But nonetheless, this market study highlighted a significant number of barriers. This could be with upfront costs, with space and water storage requirements, just a broad lack of familiarity with the technology. And, the sort of site energy savings don't typically yield operating cost savings for the facility. That's here in California. And so there's a lot of work to do. And essentially, but we really want to focus it on, well, hey, our biggest barrier is that we just can't get heat pumps in food service. And that's because of the health department. And this is not just in California. Later, we learned with a study that we're working on now that this is really across the nation. Heat pumps, there's not a path for heat pumps into the food sizing guideline. And so that's kind of what we're working on. But so this is kind of a key thing. If you want to dive in a little bit deeper, currently there's 2 formulas, one for gas water heaters, one for electric resistance. And this uses a fixed value of 0.98 for thermal efficiency. And essentially, there is not one for heat pumps. So we would be, in the simplest form, we would be oversizing by up to 400% if we use the current equation that they have in their sizing guideline. That's if that county or municipality allows heat pumps in the first place. This is the only equation they have to kind of apply that. So, there's other issues. Current sizing guidelines don't account for hot water storage capacity, which is really fundamental to how we design heat pumps. We want lots of storage and smaller heat pumps because that's where it's most affordable and most efficient. So there's just a disconnect there. And, it's a good study. We did highlight heat pump assist. This is just a way for restaurants to add heat pumps now. We have this barrier, but they can move forward by adding a heat pump assisted system, essentially developing a swing tank system. Their existing, and for illustration purposes, their existing gas water heater can become that swing tank. It can make sure that the recirc system has hot water and has good backup for the overall system, but it takes a lot of the scrutiny in sizing the heat pump for the facility. It could be sized down based on the space and electrical capacity requirements and designed in a way to run very high duty cycles. Other benefits are it could be designed to turn off during the peak periods in California from 4 to 9 p.m. and just operate the other 19 hours of the day. And so there is some opportunities here. Of course, we want to electrify fully, but this is just a way in while we still have that regulatory barrier and also a way of addressing a lot of the existing facilities we have now, which are going to have a really hard time transitioning fully to heat pumps. The other solution we highlighted was that even though we don't have a heat pump sizing guideline, we have very large hybrid water heaters that have very large electric resistance elements. This is a 9 kW, 208 volt electric resistance element, and it would work for a cafe and maybe some small quick service restaurants. And so we have solutions right now that could be utilized facilities, and they're starting to be. But nonetheless, that familiarity with the health department to allow these units is still a hurdle. So yeah, that was kind of one of the first studies we looked at, and just got the discussions going. And as mentioned, we also updated the design guide to include heat pumps. We have sizing examples in the back, and we do talk about the water heater cost and footprint using California rates. And it does also get into load flexibility. It also gets into mixing valves and water recirculators and controls. And yeah, it's available free to download from the California AWHI's website. So moving on, we are working on a heat pump assist project. This was kind of like the next level of the one we did with gas that we talked about earlier. It ended up being a very challenging project. We looked at like 300 sites, and we're only able to find a very small fine dining site. And as we've been working with that site, it's we've had some challenges with kind of getting a heat pump installed in a really old home, I guess you could say. And also we weren't able to move forward with installing the heat recovery dishwasher, just from the typical nature of this facility and the dish room. So we will still do some of the goals of this project, but the original goal was to decentralize the dishwasher, turn down the temperature of the system, which reduces the distribution heat loss rates, and then basically utilize a heat pump to electrify a lot of their hot water loads, and still rely on their existing gas water heater to make sure that we meet their full load, as well as to make sure that the health department allows us to move forward with this project. So that's still going. We'll get some results. But we did get some surprises. We were finishing up this master mixing valve project, and we were able to monitor these hybrid like commercial units in a hotel. And yeah, this project is now kind of moved from a CalNext project to a code readiness project. We're still there doing monitoring, but so this is some of our early results that we published. It really showed kind of the realities of the challenges in the field. These rooms are pretty low temperatures. There are runouts happening. System COPs, including the recirc losses, do factor in significantly. We're looking at system COP of 0.6 to 1, with a unit COP around 1.5 in these types of facilities. And yeah, if you want to look at some of the presentation at the ACEEE Hot Water Forum, there's a couple ones, 2C and 4C, that kind of talk about this project in more depth. And also feel free to reach out to me if you have any questions. Yeah, so kind of coming back, well, we do have kind of a feather in our cap, which is that although we have all these hurdles, and especially this health department hurdle, maybe we can expedite some of this. And one of the ways that's happening in California is that there are new air quality management district rules. These are in place to really reduce and prevent our exposure to unhealthy air, right? And this is including NOx and PM 2.5. The air in Southern California, Northern California, in many portions, especially in wintertime, it can be more stagnant, and our air quality index does start to increase significantly, especially when those gas furnaces kick on in the wintertime. And so the biggest news here is in South Coast, starting January 1st, 2026, with new buildings and major alterations, practically the biggest units in most restaurants or food service facilities, up to 400,000 BTUs, they will be zero NOx, and essentially gas will now be allowed as the water heater type for new construction. And later in 2029, that will kick in for existing buildings when their water heater does burn out. they will not be able to purchase a gas water heater. So that's like the biggest one. That in combination, Bay Area, which is also a large portion of the state, they start with residential um, sized heaters, which you do find in commercial spaces for like cafes and quick service. That kicks in 2027 for new construction, but really the biggest kick in is in 2031, where all the other water heater sizes are incorporated. And so essentially by 2030 timeframe, the majority of California will have to be transitioning to electric water heaters. In fact, it's 60% of the population, but only about 10% of the total area in the state. And well, why does this matter? Well, there's currently no path for heat pump water heaters in restaurants. We can talk a little bit more about that. Also, we did bring the South Coast District together with the health departments in Southern California. And what we realized was that when they passed those rulemakings, the air quality district never actually talked to the health department, or actually really looked at the food service sector, which is really kind of surprising. And when they started talking to each other, there was definitely it was like regulatory versus regulatory. And one of the responses we got is, well, if we don't trust these heat pumps, we're just going to require them to have electric resistance, right? And so what that showed was that, hey, we have a lot of work to do to get the regulatory agencies to talk together, but also to really improve, to have demonstrations and really get into restaurants. So we're ready for these regulations to kick in California. Otherwise, we're going to have exemptions, as we have had similar exemptions with reach codes and other kind of gas bans through the state, more at the city level. And we really want to avoid that for these air quality district rules that are coming in. So that's, if restaurants had to switch to electric resistance in California, that'd be a 6 times increase in their hot water bill, which, they might be paying $50,000 a year with their gas water heater currently. So that's a significant increase for these larger full service restaurants. So let's keep going. But what the I guess the motivation here is it really helps us expedite these sizing guideline revisions. It expedites doing more lab and field research and demonstrations, and it expedites really getting the industry more familiar with this technology. And what I hope it also does, hopefully it expedites some product development suited for restaurants. What I mean by that is these heat pumps are not suited for the health for the indoor application. They don't have filters suitable for the grease that's in restaurants in the air, and they're not really, don't have the ducting to kind of really help utilize the cold air coming out. We could use that to cool kitchens, right? So if we can develop the right type of heat pump water heater products, some of the additional benefits, especially now that we have OSHA in California, that's really looking at making sure people don't overheat in kitchens and in other facilities, it can really kind of address several needs at one time. So kind of moving on, because we're short on time, we're actually a little bit over our time. We have a bulletin developed. San Francisco Environment took the leadership there to develop this bulletin. We do have some health departments that are allowing variances if you monitor your system and you share that information with the health department to install heat pumps. And then we're also really collaborating, especially in Northern California, with the various health departments, SF Environment, now New Buildings Institute is part of that, and it's expanding significantly. And also on the side, TRC and others are working with health departments, focused kind of roundtable to update the sizing guidelines to allow for heat pumps to be utilized in food service. So Just my last slide is some of these studies have been completed. We're progressing with a number of studies moving forward, namely lab testing of heat pumps to mimic restaurants, and also some of the code readiness projects where we're actually monitoring heat pumps in supermarkets and hotels. And so that's kind of really exciting. And NBI and also is also doing a huge project on that as well. So a lot more to come on this. Really appreciate your time. If you'd like to get a hold of me, here's my contact details. Thank you so much. And I'll open up some questions if anyone's got some out there.
I mean, I'm really glad you brought this up. I think because it is such a big load, and especially when you add the lodging and the hotels. I think the last NBI meeting we had, AWHI had City of San Francisco or maybe somebody from the state also sharing their changes in policy. So if someone's interested in seeing that, they can also maybe know you can put it in the chat.
Just did.
Oh, lovely. Okay. Yeah, it's great. It's great that you uncovered this. It's great that we're working on changing it. So thank you.
Sure thing. Yeah.
Any other questions for Amin? Okay, then. Well, that wraps us up. Is there anything else that people would like to discuss? We did think that we would end a little early. Okay, well, with that, we'll see you at the next meeting in June. And if you ever want to reach out, present, just get more information, feel free to email below. Thank you.
Thanks, folks.
Have a good day.
Thanks.